Hello everyone, this is the lecture series of Operation Research Subject or lecture number 6, and code of this subject is ME405. This is a BTech Mechanical Engineering subject. This is a 7th sem subject, and today I will speak about the analysis in linear programming method. And for myself, Rahul Kumar, Assistant Professor of Department of Mechanical Engineering, Suresh Gyan, Jaipur. And for the sensitivity analysis problem and introduction about the sensitivity. So, sensitivity analysis is a systematic study. Systematic analysis is a systematic study of how sensitive solutions are to be changes in data, means which is the very most sensitive solution for this data. The basic idea is given to solve difficult problem into the very good manner, right? And this is the content of the today's topic. First is introduction. What is the sensitivity analysis and basic parameters. In sensitivity, duality and sensitivity, right? And the differences. These are the main topics for the today lecture. And what is the objective related to sensitivity analysis in linear programming? Objective means if any student learn this lecture, then what we will get? We will get from this lecture. These are the objectives. But sensitivity analysis is very important tool to manager who must operate in a dynamic environment with imprecise estimate of the coefficient, and sensitivity analysis allows him to ask certain what if question about the problem, and sensitivity analysis give the understanding to determine how the optimal solution is affected by changes within the specified range. Within the specified range, and these ranges are two types. First is set a objective function coefficient, and in the other way right hand side values, and in the other way right hand side values. Right hand side values. Then move to the definition of the sensitivity analysis and the post optimality. This is the second name for this sensitivity analysis is post optimality, right? So the sensitivity analysis investigates the changes in the optimal solution, providing to change the solution of the problem. Optimal solution of the problem, just select which problem related to the linear programming method. Problem related to the linear programming method, and this is resulting from changes in parameters in linear programming model. These models or parameters are objective function and constraints coefficient. Objective function and the constraints coefficient. I will give one example for this case. Suppose that you solve a linear programming problem, and then wish to solve another problem with the same constraints, but a slightly different objective function. slightly different objective functions. When you change the objective function, when you want to change the objective function, it change the objective function, it turns out that there are two cases to consider. First case, give the changes in the non-basic variables and takes values just like it is zero in the solution. For this example, here is variables are non-basic variables are x1 and x3 in this problem, or x1, x2, just like these are the non-basic variables. And then what will be happens in your solution? If the coefficient of a non-basic variables decreases, then suppose that the coefficient of x1 in the objective function above the reduced, and in this case, this solution does not change. In this case, this solution does not change. So these are the some examples related to the sensitivity analysis, right? And the basic parameter in this slide gives the basic parameter changes that affect the optimal solution R. This is the optimal solution R. These are the four types of changes. Here, four types of changes are given. First is changes in right hand, changes in cost coefficient, changes in addition of new variables, and addition of a new constant. Means some changes affect the variable problem and some changes affect the constants also, right? So this is the parameter which is used to solve sensitivity analysis problem, and for the diluted and sensitivity analysis, these are the some point which gives the better understanding about the sensitivity analysis. In the first point, no learning of linear programming. No learning of linear programming is complete unless we learn the concept of duality in the linear programming. And the second point is associated with every linear programming problem or the prime problem. Means every linear programming problem achieves the primal function. And there is another linear programming called its duality, right? Called the duality. And these two problems possess very interesting and closely related properties, which give the very good related properties. Suppose if you want to lower the objective function coefficient of a non-basic variable, basic variables, then the solution does not change, right? And what happens for this your solution? If the coefficient of basic function decreases, this situation differs from the previous one. In that you are using the basic variables in the first place. The change makes the variable contribute less profit, right? So these different types of property belongs to this duality and sensitivity analysis problem, right? And the third case is here, fourth case is here. In the most linear programming treatment, the dual is divided the best form of primal depending on the sense of optimization. And these optimization depend on the maximization and minimization of the functions and the type of constraints also and the type of constraints also. Here, lot of differences between the dual and the primal function. Dual and the primal function. Primal function always used as a maximization of the problem. Used as a maximization of the problem. But dual function always used as a minimization. Means this function minimize the solution. Right? Suppose I will take one example for a wooden industry. Any organization or just like the wooden industry or any other industry make a good product, but number of product is higher. So this is the maximization function. And if you want to reduce the initial cost, this is the minimization function. And the different type of constraints. Different type of constraints means different types of limitations are present in your organization. Suppose only you have only 10 workers, you have only this amount of money, and you have only limited area in your warehouses. Means storage space is less and less availability of the skilled worker, less availability of the skilled worker. These are the constraints related to this problem. So different types of constraints. Some constraints are very sensitive. Some constraints are very sensitive. Sensitive means labor. Suppose in the in this problem or in this example, labor is a very sensitive element. Labor is a very sensitive element because all things all things depend on the labor. Depend on the labor in your factory. If your worker and labor is satisfied, then all things are will come into a positive manner. Otherwise, all things goes on the uh, just in the loss of the property, right? So this labor is very sensitive part of any organization, right? And primal and dual relationship. Primal and dual relationship. This gives the relationship between them, primal and dual. In the primal case, maximization. Uh, Primal and dual differences I will start in the previous lecture, next lecture number 5. So primal and dual, what the difference between two of this? It shows the maximization of the function. For the dual, it shows the minimization of the function. Here the number of variables are limited, but here the in the dual function number of constraints is limited. Here number of constraints and number of variables and objective function values. And here is right hand side values are always varying, right? And coefficient matrix for constraints. Here the transport of the constraint coefficient matrix, right? Here the variable is less than equal greater than equal variable, and here the constant is greater than equal constant. Here the less than equal. If same problem, this is a this case, then here is just opposite. Or unrestricted variables, here the constant is an equation. Here this greater than equal to constant and less than equal to constant. This is the equation and unrestricted variable. This source I have taken from Nepter learning program and source PD, right? So this is the one example for this analysis here. So for the example of this, we formulated and solved the linear programming problem to maximize the revenue for the bakery. The problem is to just like as a maximize. This is a primal problem. This is a if you want to maximize the profit of the any organization, then this is the primal problem, and this is the minimization case for the duality problem, right? Then the maximization is 32x1 plus 25x2, and these are the two constants 5x1, 4x2 less than equal 59, and 4x1, 3x2 less than equal 46. Here x1 and x2 greater than equal 0, and the optimal solution obtained using the solver. Optimal solution obtained using the solver is x1 equal to 7 and the x2 equal to 6 with z equal to 374. So this is the optimal solution for this problem. And for the minimization case, you, for the solution of this question, you can already solve different types of problems, right? Related, similar to this problem. And in for the minimization case, here the objective function is 59 by 1 plus 46 by 2. 59 by 1 plus 46 by 2. For this case, the constants are here 5 by 1 plus 4 by 2 greater than equal 32. And this second constant is here 4 by 1 plus 3 by 2 greater than equal 25. And the by 1 by 2 greater than equal 0, right? Means all y1 and y2 values taking as a positive value. The optimal solution for this problem is here y1 equal to 4 and y3 equal to 3. The optimal solution for this problem is here y1 equal to 4 and y2 equal to 3 with the objective function value w equal to 374. W equal to 374. So points are different, but value of this problem is same, right? This function maximization and minimization function is same value. So this is the different question and this is the different question. Just do not relate these two values, right? So this is the one question. Means one examples for the case of right? Now considering the maximization problem called P1. This maximization problem, this is called P1 and this is a P2 problem, right? We make the following observation. P1 and P2 had the same values. P1 and P2 had the same values of the objective function at the optimal, just like the Z equal to 374 and W equal to 374. W equal to 374. The objective function coefficient of P1 are RHS value of P2 and vice versa. Then for the minimization case, 59 plus 46y2 subject to 5y1, 4y2 greater than equal to 32. And then in this case here, just like this, this is the representation, right? Right, like so these constants are two types, right? And then move to the third step. The number of variables is in P1 and the number of constants in P2, which is the case of maximization case. 5x1 plus 4x2 less than equal 59. And 4x1 and 3x2, this is equal to greater, less than equal to 46. Is there a relationship between P1 and P2? The relationship is established using the discussion as follows. Consider P1 the maximization problem. If there were no constants, the objective function value is infinite. The objective function value is infinite, right? Let's us to try get upper estimate for the value of Z. So consider P1. The objective function value to get the upper estimate value for the value of Z is here. So these are the two functions. This gives the different types of constants by 9. Right? Here we will multiply the constants by 9. Okay. Just note down this and we multiply the second term. Then the constant function is it will like as a 36x1 plus 27x2 less than equal 414, and since x1 and x2 are less greater than equal 0 and the function is maximized function, just write like as a 32x1 plus 25x2 subject to 5x1 plus 4x2 less than equal 59 and 4x1 plus 3x2 less than equal 46. These are the constants. And for these two constants gives the value of z function is here 414. This is the value of 414 is here. So we multiply the first fraction by 7, it will get it just like it is this 413 and then 414, right? So we add two constants to get 9x1 plus 7x2 greater or equal 105. This is inequality holds because x1 and x2 are greater than equal 0. Then 9x1 and 7x2 less than equal 105 into x4. We multiply this constant by 4 to get 36x1 plus 28x2 greater than equal 420. Since x1 and x2 are greater than equal 0 and 32x1 plus 25x2 less than equal 36x1, this is a greater than equal 420. So therefore 420 is an upper estimate of Z star, upper estimate of the Z star. But we ignore this because our current best estimate is 413. Best estimate is here 413 in this case, right? Then we multiply the constants 4x1 plus 3x2 less than equal 46 by 25 by 3 to get it will get a this type of value, and this will give a Z 377.6 is the better upper estimate for Z star. So based on the above discussion, 377.6 is the better upper estimate for Z, right? And if we want to put here 32 by 5, then you will get a 377.6. And if we will multiply it by 25 by 7, you will get a value of 375, right? So now 375 is the a better estimate for Z star. So these values are always changing depend on the constants. So this is the sensitivity analysis. If any function, so this is a minimization problem. Which function on which value gives a very minimum or which constant provide a very minimum function value. This is the solution of your answer, right? And then we therefore define A and B to minimize 59A plus 46B is minimized, right? So this is the sensitivity analysis problem for this lecture. And then move to the second question. And then move to the second question. This is your maximize function, which is Z equal to $100 x1 plus $50 x1, and this question subjected to 1x1 plus 2x2 greater less than equal 40. These are the two types of constraints, and this solution you will solve by a graphical method. You will solve by a graphical method. So what will happen here? So this is the Z function value. This dot sign shows the Z function. And these are the two type of constants. These are two type of constants value. And here the feasible region is here A, B, C, 0. Right? This is the feasible region. And the optimal point for this case here, this is the optimal point. Right? So this is the optimal point. For this case, 30. 30, if you take x equal to 30 and x2 equal to 0, then it gives a Z function value is here 3000. So 30 and it will get a 3000, right? You can move to the next step here. If you put this value, this b optimal value, it will get a x1 equal to 24 and x2 equal to 8. These values are z equal to 1360 1360 for this point, but in this case z is here, right? And then we move to the next step and put these optimal point, x1 equal to 0 and x2 equal to 20. Then the value is here z equal to 200. So what will be seen here? Here if I am putting this first c value, this is a x1 equal to 30 and x2 equal to 0, then you will get a maximum function value is here 3000, right? In this case, but in this case here the maximum function value is just like as a 1360. This is less than the this optimal solution, right? This is the less than the this optimal solution. And if I am taking this a optimal solution, so here it will give a 2000 value. So for the maximization case, maximization case, the better optimal value gives this point c. So c is the right answer. But here all values are variable. So, sorry. So for the sensitivity range is here. For the sensitivity range, 4 less than equal C1 and less than equal infinite, and 0 less than equal C2 less than equal 4.5. It will give say slope of minus 4 comma 3, 4 by 3, and this is, it will give say slope of minus 2, right? And this A point, here this A point gives a value of maximum minimization function value is 24, right? This is the 100. Oh, sorry for this. This is the second question, right? And this question is solved, and here the maximum function value is z equal to 3000, right? Z equal to 3000. So this is the second question. Here the minimization function problem, or this function related to the duality analysis, right? Subjected to the constraints 2x1 4x2 less than equal greater than equal 16, and 4x1 plus 3x2 greater than equal 24, x1 x2 greater than equal 0, and the sensitivity ranges 4 less than equal c1 and less than equal infinite, and 0 less than equal to c2 and less than equal to 4.5. It gives the value of x1 x2 x3 just like that equal to 24 is here. So the sensitivity case, the sensitivity range for the right hand side value is the range of value of which the quantity right hand side values can be changed without changing the solution variables, mix including slack variables also. And any changes in the right hand side of the behind constraints will change the optimal solution, right? This is the right sentence. And any change in the right hand side of a non-binding constraint that is less than its slack or surplus variables will cause no change in the optimal solution. This is the shadow pricing example. This is the shadow pricing example. And next one is reduced cost. These are the points related to the reduced cost here, right? And then move to the next MCQ problem. Move to the next MCQ problem. Here the operation research study generally involves how many phases? Operation research generally involves how many phases of this problem? 3, 4, 5 or 2? For this, correct answer is here 2. Then move to the next problem or MCQ. Yeah, this is the blank space. Model involves the allocation of resources to activities in such a manner that some measure of effectiveness is optimized. Manner that some measure of effectiveness is optimized. First one is sequencing, allocation model, giving theory, and decision theory. So, what will be the right answer for this question is here? Is the allocation of the model. This is the right answer. All right. Move to the next question. 30. Uh, third question. Sorry. And wait for some time because okay, sorry for disturbance. Problem related to the laptop battery. Then allocation problem can be solved by can be solved by for this correct answer is C. C is the correct answer, right? Non- Non-linear programming techniques and linear programming techniques are to use the allocation problem can be solved. Fourth question in models, everything is defined and the results are certain. Deterministic model, probabilistic model, both A and B, and none of the above. Then the model is here. Correct answer for this question is A. Right? In models, there is risk is uncertainty. There is risk is uncertainty. This is the correct answer for this question is 30 probabilistic. Right? The model are obtained by enlarging or reducing the size of the eye. Iconic model, analogy model, symbolic model, and none of the above. This is the iconic model, right? And in the seventh case, operation research attempt to find the best and solution of this problem. Optimal, perfect, degenerate, and none of these above. The correct answer for the question is optimum case. Right? The word may be defined as some action that we apply to some problem. Hypothesis, research, operation, both A and B, and none of the above. Operation. This is the correct answer for this question. For the ninth question, the operation research techniques especially used to determine the optimal strategies with the help of simulation. The operation research techniques which help in minimizing total waiting and service cost is here. What is this? Correct answer is queuing theory, decision theory, both A and B, and none of the above. Both and A and B, and none of the above. The correct answer for the question is queuing theory. Right? Queuing theory is the correct answer. So this is the MCQ questions related to this top lecture, and then these are the references. Operation research and introduction of ninth edition, person education, and the second is theory and practice, engineering optimization, and the operation research applications, and the national program on the national technology and NEPTEL by Professor G. Srinivasan. Right? So these are the references of this lecture is here, and thanks for this lecture. I will discuss in the next upcoming lecture. I will discuss the topic about the some problem related to data analysis and graphical method, and some problem programming ability nature problem. Right. So thank you all of us.